This lecture we are going to continue about the pipelining. So back then we had seen one analogy or one real world example of pipelining and how Henry Ford had started all those pipelining technique and everything. And here this is the definition, exact definition according to the computer organization. So pipelining is a technique where multiple instructions are processed in overlapping stages like an assembly line to make the execution faster. See this assembly line, this particular line, assembly line, this is where the technique was called back then, which Henry Ford had invented for the industrial revolution. That technique was called assembly line. From there only the pipelining technique has derived. Okay, anyway, this definition I don't think so you will understand this now, right now. So we will take one example and after that you will understand properly this definition. Okay. Now the main thing about pipelining is why we are using it, because using a pipeline we will able to execute more than one instruction. Can you see that? More than one instruction at the same time. This is where the parallelism came into picture. Okay, so this is because of this only, more than one instruction executing at the same time. Because of this thing it will simulate like a parallel processing, right? Fine. So before getting into pipelining concept, you have to understand about the basic instruction cycle. Okay, what it is exactly. So we know that whenever we try to execute any instruction, okay, CPU execute that instruction, each instruction in 4 phases. Okay, so that 4 phases is instruction fetch, instruction decode, execute, and write back. So you can see here, see what will happen is, so you can see here whenever CPU try to execute this instruction, this particular instruction I1, then it will go through first phase, that is instruction fetch cycle. Okay, in this what will happen is this instruction 1 will go through, for example CPU is trying to execute I1, so it will go through this first phase, that is instruction fetch. So what this instruction fetch says is that instruction is fetched from the memory. That means this instruction will be kept inside some memory, that from the memory it will be kept inside one register. Okay, so whenever CPU try to execute the instruction 1, first phase is instruction fetch. In instruction fetch what will happen, CPU will take this particular memory, CPU will take this particular instruction and will keep inside this particular register, that is instruction register. Okay, which is inside this fetch cycle. Okay, so that is called instruction fetch. Just take this I1 and keep inside the instruction register. Okay, that is called fetch. So this is called instruction fetching. Okay, after this phase is over, instruction 1 will get into instruction decode phase. Okay, in this decode phase what will happen is it will analyze the instruction. Okay, what kind of instruction it is, like we had already seen about addressing mode. So that same thing will happen in addressing mode. What we are doing it, we are analyzing the instruction, what kind of instruction it is it a immediate addressing mode, is it a indirect addressing mode, is it a direct addressing mode, is it a relative addressing mode. All those analysis will be happening here in this instruction decoding phase. Okay, then after that instruction I1 will move to instruction execution phase. Okay, in this phase what will happen, whatever the operation you are defined in the instruction like addition, multiplication, whatever you want to perform, that will be performed in the execution phase. Here it will be taken care by ALU will come into picture and they will take care of execution phase. So they will do all the whatever the operation you had mentioned in the instruction. If it is an add, it will do addition. If it is a multiplication, it will do multiplication. All this thing will be happen in execution phase, right? This will be taken care by the ALU. See, all this thing I hope you already knew it. We had already seen it back then also. So I'm not going to explain in a deep way. Just try to understand, okay, whatever is necessary. Now in this phase will what happen, I1 will move to, after execution it will move to a write back state, which is a storing part. So in this phase what will happen is the result is stored back in the register or the memory. Okay, what does it mean is whatever the result is generated, right, that will be stored back in the accumulator, or it will stored back into some other register, or whatever the result is generated, that will be again stored back inside a memory itself. So that process is done here in write back. Fine. So whatever instruction we are trying to execute, or a CPU is trying to execute, first it has to go through all the process to complete its processing. Then only we can say that one particular instruction is executed or is processed. Okay, after going through all these phases. So we have to take this thing also. We have to understand this part also, right? Now you have to understand one more thing, that is all about system clock. Okay, so the thing is, the CPU works based on system clock. Okay, uh, what does it mean is, for example, we had seen all these phases, right? Instruction fetch, instruction decode, execute, and write back. All this phase will take some time, right? Whenever instruction is getting into this phase, it will take some time, right? We don't know that time, what is the time is, right? And that is decided by the CPU, system clock. Okay, so suppose here in this example, just to make the concept simple, what I'm assuming is, I'm considering that each phase will take one clock cycle. Okay, this will also take one clock, means one cc, like you can consider. This will also take one clock cycle. This will also take one clock cycle. This phase will also take one clock cycle. So each phase will take one clock cycle. I'm just assuming it, just to make all these concepts simple, right? So each phase will take same clock cycle. Okay, one clock cycle. Now you might be wondering that one clock cycle, okay, that is fine. But what is the measurement of this clock cycle? What do you mean exactly what by clock cycle? For example, if I ask you 1 hour, 1 hour means what is the measurement? 60 minutes, right? So you know that 60 minutes means 1 hour. But if I talk about one clock cycle, what is the measurement? So to understand that, we will see one thing, that is clock. See what exactly clock look like. We had already seen this, right? This entire thing is one clock, right? This entire thing is one clock, or you can call it as one clock cycle, right? Now the question is, what is the measurement, what is the time period of this clock? So how can you calculate it, right? So for that you have to understand one thing, that there is one measure, one parameter will always be given for this thing. If the time period is asked, that is frequency. For example, in this case I am assuming the frequency is 1 megahertz. Okay, so I don't think so you, if you're not from you might not understand what this megahertz and everything. So for that we will brush up some concept. For example, you have to understand one thing before understanding all this thing. Here mega, m is written, right? Megahertz, right? So m means mega, right? So there is something, some terminology called k means kilo, right? And it is 10 raised to power 3. Just remember this thing. Mega, m means mega, so mega means 10 raised to power 6. Giga, g means giga, so giga means 10 raised to power 9. So this thing you have to remember. Okay, this is few things you have to memorize it. And one more thing is, just to, so that it will be very easy for me to explain the concept and to solve some problems which is going to come right now. Now 1 megahertz. So one thing you have to understand is 1 hertz is equal to 1 upon second. This is one thing you have to understand. So I can write, therefore I can write 1 second equal to 1 upon hertz, right? Now one more thing is millisecond, microsecond, nanosecond. You have to understand that thing also, right? So 1 second is equivalent to 10 raised to power 3 milliseconds. Okay, this is called millisecond. And 1 second is equivalent to 10 raised to power 6 microsecond. This is the donation. This symbol denote microsecond. Okay, so microsecond. And 1 second is equivalent to 10 raised to power 9 nanoseconds. Okay, small n, nanosecond, right? So to make it simple, you can understand like this. For example, 1 millisecond, 1 m, or you can write it like this. For example, small m denote 10 raised to power minus 3. That's it. You remember this thing. Either you remember this part or you remember this part. Or small u micro, it denote 10 raised to power minus 6. And small n denote 10 raised to power minus 9. Okay, this part you just remember it. Okay, you will come to you will understand why I am doing this thing when we solve one problem. Okay, so you try to remember this part. Okay, then it would be very easy for me to explain the concept and you to understand the problems and everything. Okay, and it will be very easy when you are solving the problems also. Okay, now coming to this part, frequency equal to 1 megahertz, right? Here frequency is already given. I have to calculate a time period. Okay, that measurement of this one clock means what is the time period. So for time period, which is denoted by t, we have already have one formula, that is 1 upon frequency. Fine. And we already knew that frequency is already given, right? 1 megahertz. Right. Now you try to calculate, you try to put it everything. 1 into mega means what? You can see here. Mega means 10 raised to power 6. Hertz. You can't do anything here. So can I write 1 into 10 raised to power 6 like 1 into hertz? Yeah. Now you can clearly see 1 into hertz means 1 second. Right? Can you see the correlation? So how can I write is, I can write this like this. 1 into 10 raised to power 6 into this part will become second. Now I will take this into 10 raised to power minus 6 second. Right? After solving it. Now you observe carefully, 10 raised to power 6 seconds, 10 raised to power minus 6 seconds. That is the time period what we got here. Right? Now this 10 raised to power minus 6 is what? Can you see? That is u. It denotes u. So can I directly write u here? Right? I can write, right? So if I write it, then it will become u. Instead of 10 raised to minus 6, I will directly write u, and this become microsecond. It is equivalent to 1 microsecond. Right? So this is what we got. 1 microsecond. So what does it mean is that the time period of this entire one clock cycle is 1 microsecond. Okay, which is equivalent to 10 raised to power minus 6 second. Okay, that is what we derived it. Okay, I hope you understood, right? So with this we understood that our time period is 10 raised to power minus 6, that is 1 microsecond. That means each phase will take one clock cycle. What is the meaning of it? That it will take 10 raised to 1 microsecond, that is, which is equivalent to 10 raised to power minus 6 seconds. Each phase will take 1 microsecond. This will also take 1 microsecond. This will also take 1 microsecond. This will also take 1 microsecond. So each phase will take 1 microseconds. Okay, that means whenever instruction get into this any of this phase, it takes 1 microseconds to complete that particular phases, or to complete that particular stage. Okay, after 1 microsecond it will come out of the particular stage. That is the meaning of it, right? So hope you understood. So in this lecture I just want to show you how all the when with pipelining or without pipelining, how instruction will go through all the phases. Okay, now what I will do in next lecture, because this video is already getting very long, so in next lecture I will try to take one example directly and try to explain you how when one instruction will go through all these phases with and without pipelining, how can you improve the performance. Okay, so without pipelining what would be the performance, and with pipelining how you can improve that particular performance. Okay, when one instruction will go through all these phases, right? So that I will cover in next lecture. Fine.